So good morning, esteemed colleagues and friends of the University of Illinois, Chicago, the University of Illinois, Urbana-Champaign, and the University of Illinois, Springfield. Welcome. Buenos días, estimados colegas y amigos de la Universidad de Illinois. Bienvenidos todos. Bienvenidos investigadores de varias instituciones de México y de otros países latinoamericanos. A special welcome to students and to distinguished researchers from different institutions. Gracias por su distinguida presencia. We appreciate your presence. Happy Independence Day to Mexico and Central American countries. My name is Elvira de Mejia. I'm a professor at the University of Illinois in Urbana-Champaign, and I am the director of the University of Illinois System Initiative, I-MMAS, Illinois Mexican and Mexican-American Student Initiative. Welcome to the second Symposium on Energy that the University of Illinois Mexican and Mexican-American Student Initiative organizes. I'm humble and thankful to facilitate this important and urgent initiative. I thank the President of the University of Illinois, Dr. Timothy Kalin, for his leadership and enthusiasm, recognizing the need and the opportunities that I-MMAS presents. You know, I-MMAS represents a culture of support, building pipelines for Mexican and Mexican-American students, smoothing the path and retaining as many talented students as possible. Building a network of collaborators, that's key. I-MMAS is about partnering in collaboration with our peers in Mexico. I-MMAS will enhance ongoing efforts by the system's 3 universities, Chicago, Urbana-Champaign, and Springfield, to expand Mexican and Mexican-American educational opportunities. I-MMAS' vision is to promote a more extensive network of Mexican and Mexican-American scholars at the University of Illinois system, with synergistic opportunities for research, professional development, student support, while we're fostering a more equitable workforce of well-educated professionals, capable to succeed in life and providing solutions to pressing challenges in Mexico, in Illinois, and around the world. I feel proud to be part of the second I-MMAS Symposium on Energy with the participation of distinguished researchers from the University of Illinois and distinguished researchers from UNAM, Mexico, and the Universidad Tecnológica de Querétaro, Mexico. This symposium was organized by Dr. Leonardo Chamorro, Associate Professor at the University of Illinois, Urbana-Champaign, an outstanding researcher and outstanding engineer. I was impressed by his publications in Nature, Science, etc. And also by a distinguished professor and researcher, Dr. Victor Castaño, researcher at the National University of Mexico. So 2 outstanding scholars are organizing this symposium. The symposium, Opportunities and Challenges in the 21st Century, will highlight cutting-edge research, including the impact of renewable energy. As a matter of fact, yesterday, September 14, we had extraordinary presentations on renewable energy. If you miss it, please check back in the I-MMAS website that we will send it to you now in the chat. In a few weeks, we will have the recording of the symposiums and you will be able to enjoy it. It was fantastic. Today, the symposium is on sustainability and climate change. The objective of this symposium is to enhance strategic synergies among researchers in Illinois and in Mexico on renewable energy, sustainability, and climate change. We thank all authorities and representatives of different institutions for their presence and remarks. And it's a great distinction to introduce J.D. Richard Winkle, Deputy Executive Director of our own Prairie Research Institute, University of Illinois, who is joining us with welcome remarks. He has a BA in economics from the University of Illinois at Urbana-Champaign, and he earned his law degree at DePaul University College of Law. Dr. Winkle, or J.D. Winkle, is a co-author of a book entitled Illinois Politics, published by University of Illinois Press. Check out our website on the Prairie Research Institute, and you will see that has different divisions on natural history, archaeology, geology, water survey, sustainable technology center. So now we have here the welcome remarks from J.D. Richard Winkle.
My name is Rick Winkle. I'm Deputy Executive Director of the Prairie Research Institute at the University of Illinois. And it is my pleasure to be here today with you to hear about the important collaborations before us and to learn more about the innovative strides that you are all making in your respective fields. But first, I want to thank all of the extraordinary sponsors, speakers, and esteemed guests for their hard work and support. Without all of you, this symposium would not be possible. We are here at a critical moment when the need has never been higher to create a robust and sustainable energy economy. At PRI, our mission is to conduct transformative research that benefits the people, the economy, and the environment of Illinois and the world. That mission is demonstrated by our pioneering work in carbon sequestration, which led to nearly 1 million metric tons of CO2 being stored in the Illinois basin, and creating some of the world's richest data sets on geological characterization of the subsurface. We are working with local power generating companies like City Water, Light, and Power in Springfield, Illinois, to construct one of the world's largest carbon capture pilot systems that is leading in the net zero efforts to slow the effects of changing climate. PRI is leading in the carbon capture projects across 10 states in the US and is helping industries explore ways to utilize the captured CO2 to grow algae that are used for animal feed, to create biofuels, and to enhance cement production. We are leading in the charge to meet the need for renewable energy, such as geothermal, and exploring Illinois as a source of critical minerals to help accelerate the clean energy transition. We like to say at PRI, our research is not only happening in a laboratory, it is happening out in the world. Bridging discovery research with societal applications and impacts. And at PRI, we get it. We understand that partnerships across governments, industries, and universities worldwide are essential to drive innovation. Collaborations like this one will play a significant role in overcoming the unprecedented energy, sustainability, and climate challenges before us. We look forward to learning more from all of you in the upcoming presentations. Thank you.
Now we have the remarks from Dr. Guillermo Pulido, the director of the National University of Mexico in Chicago, UNAM, Chicago. He's an alum from UNAM from the College of Economical Sciences, and since 1980, he has been a professor and researcher on fields related to economy, political sciences, and international relations. His work has contributed to the establishment of UNAM sites all over the world, including Chicago. Dr. Pulido is a great collaborator of the University of Illinois system. So now we have his welcome remarks.
Ladies and gentlemen, good morning. With a great sense of purpose, I'd like to welcome you all to this academic symposium organized by the Illinois Mexican and Mexican American Student Initiative. Focus on the pressing issue of our time: climate change, renewable energies, and sustainability. Thank you, Dr. Elvira de Mejia, for inviting me to share with the audience a few thoughts. As we gather here today, we stand at a critical juncture in human history, where the choices we make have the power to shape the future of our planet and the generations to come. The topic discussed over the course of this symposium are not mere subjects of scientific inquiry, there are urgent calls to action that demand our attention, collaboration, and innovation. Climate change, far-reaching impacts are no longer theoretical scenarios, but the stark realities felt across the globe. From changing weather patterns to rising sea levels, from the biodiversity loss to extreme weather events. Just remember, a few weeks back, the incredible damage caused by the fires in Maui or the devastation of the Canadian forest. Yet, in the face of these challenges, there is a hope that springs from the transformative potential of renewable energies, which offer us a pathway to more sustainable and harmonious coexistence with the environment. The strides we made in harnessing solar, wind, and other renewable sources remind us that the human ingenuity knows no bounds. Sustainability in all its dimensions is the bedrock upon which we must build our strategies, policies, and technologies. It is about recognizing the delicate balance between our societal needs and the Earth's capacity to provide it. It involves remaining how we are consumed, produce, and interact with our surroundings to ensure a thriving planet for our present and future generations. I was very glad to learn recently from President Timothy Kailin during the Council meeting of Discovery Partner Institute that Chicago will be the host city in 2025 of the Conference on Sustainability, Research, and Innovation, which unites global leaders in research, governments, civil society, and business to meaningfully advance progress towards sustainability. This is an exceptional, inclusive, and inspiring global platform for co-creating state-of-the-art solutions and innovations, and building a coalition of the willing to achieve a sustainable transformation. As we embark on this intellectual journey together, let us open our minds to new ideas, engage in meaningful discussions, and foster collaborations that contribute to a real-world change. The presentations, dialogues, and exchanges that you will unfold in the coming 2 days hold the potential to spark breakthroughs and inspiring actions. As we immerse ourselves in the symposium, let us remember to each contribution, no matter how small, bring us closer to a more sustainability future. I encourage all of you to actively participate in our collective efforts that can contribute to navigate the challenges of climate change and curb a greener, more equitable world. Thank you for your dedication to these vital issues, and I eagerly anticipate the impactful discussion that lies ahead. Together, let us be the catalyst for positive change and leave a lasting legacy of environmental responsibility. Thank you very, very much. Muchas gracias por su atención.
Thank you to all of you for your kind words. It is my pleasure to introduce Dr. Victor Castaño, professor and distinguished scholar from the National University of Mexico, UNAM. He will be the moderator of today's session of the symposium. Dr. Castaño is the co-organizer of this symposium with Dr. Leonardo Chamorro, associate professor at UIUC. Dr. Castaño is a very accomplished researcher, and we thank him for his leadership and extraordinary contributions to the organization of this symposium. I thank all the speakers. I hope this symposium will spark new collaborations, new discoveries, and then many problems will be solved. Thank you. Dr. Castaño.
Thank you very much. Good morning and welcome to this second day of this important event. I would like to thank again the University of Illinois Initiative, and in particular Professor Elvira de Mejia, and of course the hard work and stamina of my organizer, Professor Leonardo Chamorro. Today we will have a very exciting day addressing sustainability and climate change, which are two of the key concerns of the world today. To accomplish this, we have invited four distinguished speakers, and today we feel more generous than yesterday. So today, every speaker will have up to 20 minutes to deliver their presentations, including questions. We will also have at the end around 20 minutes to address some questions that the audience could have, and also to wrap up the meeting and make some plans and accept suggestions for the future events. It is my pleasure then to introduce Professor Kyle Smith from University of Illinois. Professor Smith, you will have up to 20 minutes for your presentation. Thank you.
Thank you very much, Professor Castano. I'm happy to be here today. Thank you to Professor Chamorro and Professor De Mejia for inviting me. Today, I'm going to talk specifically about a sustainability challenge dealing with water. So less so about climate change and more about water and our need for it as humans, and some particular work that my group has done to develop devices that are unconventional for desalinating water. And I'll just mention that this work was funded by the U.S. National Science Foundation, as well as it's being currently funded by the U.S. Office of Naval Research. There's a few different key points that I have you to take away from my talk here. I know this is somewhat of an eye chart to start with, but the first is the motivation. Water scarcity, especially under climate change, is going to be an issue of increased significance in the future, and desalination is one way to address that by increasing access to freshwater resources. My group is exploring how to do this using electrochemical approaches that leverage knowledge from the battery world, essentially, to do it. But what I'm going to show you is that when you attempt to use a battery-like device to remove salt from water, in particular when you're flowing the water through this battery, the way in which the battery cycles is very different than how it would cycle if you were using it to store energy. And as a result, we have to think about how to engineer these batteries to allow flow to occur efficiently through them. And I'll tell you that by using that kind of knowledge, and developing solutions based on it, now we've been able to desalinate seawater level salt concentrations for the first time using a process like this. But also there's opportunity to apply what we've learned concerning the engineering of electrodes for flow to other types of devices for energy and sustainability applications, including fuel cells, flow batteries, and electrolysis cells. Okay, so without further ado, let me go ahead and step into the first point. So the diagram that I'm showing here on this slide shows a map of the water scarcity metric. This analysis was done back in 2016. And here, water scarcity is defined as the ratio of freshwater consumption to freshwater availability. So the bigger this ratio is, the more of a deficit of water availability or water resource there is. Hence, it's called water scarcity. And in particular, values above 1 are particularly problematic. And if we just look at the globe here and all the landmass on it, what it indicates is that more than 60% of humans on Earth experience extreme water scarcity for more than 1 month during a given year. And of course, the oceans which surround the landmass have an abundance of water, but salt contaminates them, and that's toxic for humans. If we zoom in on Mexico, Mexico is one of the hardest hit regions in this regard. You know, there's water stress that's induced directly by climate change, but there's also human-induced factors due to consumption of water from the Colorado River by folks in the United States in the western half of our country. So there's a lot of complex issues around that, but desalination is one strategy that could be used to help alleviate these issues of water scarcity. So if we look at different types of feed waters that might be used as sources to produce fresh water from by way of desalination, they take different amounts of energy to desalinate the water from them. On this plot here, what we're showing is the actual energy required to desalinate water from a given source divided by the thermodynamic minimum value. So thermodynamics tells us the absolute minimum amount of energy that it would take to desalinate water of a given concentration. But even for the feed water that has the lowest energy consumption ratio relative to thermodynamics here, it's still more than 5 times more than the energy consumption required by thermodynamics. So what that shows us is that there's a lot of room for improvement. And clearly this is important in the context of sustainability as well, because if we're using energy to desalinate water, we want to use very little energy, one, on the basis of cost, that is the economics that we're working around, but also if the energy is produced by non-renewable resources, then there's some carbon footprint associated with that energy use as well. So ideally, you want to have as low of energy consumption as possible. And in addition, if we look at global desalination capacity, both by the source of the water that is used to desalinate water from, as well as the technology that's used to desalinate it, seawater desalination by reverse osmosis is the predominant installed capacity in the world. But another sustainability aspect that is inherent to desalination processes is that you have some waste product, the salt, that is formed as a result of making the desalinated water. And reverse osmosis in particular is limited in terms of how much brine volume that it produces as a byproduct of desalination as a result of the osmotic driving force or the hydraulic driving force that's required to overcome osmotic pressure across the semi-permeable membrane. So that means that for every unit of water volume, desalinated water volume that is generated, 1.5 units of brine are generated. And you have to dispose of that somewhere, right? That's going to have ecological impact somewhere, right? So in principle, you want to reduce that brine volume production. Right, so I started looking for alternatives to desalinate water using electrochemical approaches, which leverage a different kind of driving force than the hydraulic one that is used in reverse osmosis back in 2014. And in short, the first piece of work that we came out regarding this back in 2016 was actually a modeling work. We used computational theoretical modeling to show that if you were to make a battery, in this case, a battery that uses electrodes that absorb sodium ions and release sodium ions, while those sodium ion absorption materials are separated by a membrane that is only selective toward the anions, that would be the chloride ions in a salt water solution. And if you flow the water through the electrodes, you can generate one stream of desalinated water simultaneously with one stream of concentrated salt water or brine. right? So this got a lot of people thinking back in 2016, thinking in a different way about how to desalinate water, because until that point in time, almost exclusively when electrochemical desalination was used, electric double layer capacitance was used as a mechanism to store charge. And electric double layer capacitance stores charge at the surface of electrodes. And hence the amount of charge or salt that can be removed ends up being proportional to the surface area of the material in the electrodes. Whereas when we use this battery-like architecture, it allows us to use bulk solid storage of sodium that is proportional to the volume of the active material that is inside of the electrodes. And hence, in principle, this sort of approach should be able to desalinate far beyond seawater level salt concentrations. Right, and so I represent that on this plot. So if we have a sodium ion battery material that has a charge storage capacity of 55 milliamp hour per gram, and it has a density of 2 grams per centimeter cubed, that corresponds to a storage concentration of sodium in the solid state of 5 molar. That's 10 times the concentration of sodium that's in seawater. So in principle, you would expect this to desalinate seawater and lots of other things that are more concentrated. And our initial modeling showed that we could do this. But in practice, when we started doing the experiments back in 2017, we removed 0.5 millimolar of salt from 25 millimolar salt concentration, which is tiny. And despite that minimal effort, we learned a lot, I would say, in the process. We started thinking about how the transport phenomena occurs in these systems, in particular by using flow of the electrolyte through our electrodes rather than by them, and also optimizing the formulation of the conductive additives that were in electrodes were in our electrodes. We increased the salt removal by 100 times. And then by recirculating the water through our electrodes and using very high capacity electrodes by making them very thick, we increased it by another 4 times. And then most recently, by embedding microchannels into our electrodes, we increased the salt removal by another 5 times to get us up to this seawater level desalination salt removal. Right, so let me just talk about those different ideas here. So as I mentioned, the way in which the flow channels in the device are arranged with respect to the electrodes matters. This plot here is generated by way of simulation, but if we arrange our electrodes or our flow channels behind our electrodes using a so-called flow behind configuration, like what I'm illustrating here, basically the salt ends up depleting inside of the electrode. That is the compartment here, which has the deep blue color. And because the flow is happening behind the electrode rather than within it, that desalinated water just stays inside the electrode, right? So even though it's desalinating somewhere in the device, the process is not producing that desalinated water. And likewise, if we put the flow channel in between the electrode and the membrane, we get a similar effect. You get pronounced desalination inside of the electrode where flow is not occurring, and much milder desalination inside the channels. Whereas in flow through, you get the desalination in the compartment where flow is occurring. It evacuates the liquid from the electrodes so as to maximize the salt removal. I'm going to move fast through this for the sake of time, but I'll say that another thing that we learned along the way is that by recirculating the water through our electrodes, it allows us to independently control the flow rate of the electrolyte while maintaining a certain level of salt removal. And by doing that, we can mitigate what I call state of charge gradients or reaction reaction non-uniformities that result from the coupling of reaction rates to salt concentration. And together with that, when we recirculate our water through our electrodes, we have to be very careful about how we time the application and switching of current with the switching of valves. So in this movie, which I'm showing here, we developed a valve switching apparatus where we first switch our inlet valves, then we have a delay, and then we switch our outlet valves in sync with the current switching events. And as a result, we have in one electrode water that desalinates, then we switch, and then water desalinates in the other electrode. But it happens in a kind of pseudo-continuous fashion. Right. So this gets me to the primary work that I'm going to talk about today, because up until this point, even with these advancements that we made in terms of flow-through electrodes and using recirculation through the device, we were still limited to brackish water desalination. The salt removal was on the order of 100 millimolar or less. So we started thinking about how the dynamics of this recirculation process could be influencing the salt removal of the device. And we also observed then when we collated all of the data using cell architectures like this to show salt removal versus the capacity of the electrodes, there was a correlation between these two quantities. As we increase the electrode capacity, salt removal in general increase. So that really motivated us to just make bigger electrodes by having a larger area in order to remove more salt. And ultimately, that's what we ended up demonstrating in the work that I'll show you. That's how we got up to seawater level salt concentrations. But the challenge in making bigger electrodes is that you increase the flow path length through which the fluid has to flow when you have bigger electrodes. Hence, pumping pressure is greater. And if our pumping pressure is too big, then we might as well do reverse osmosis, right? So the way that we addressed that here was by embedding microchannels in our electrodes. So in particular, the kind of microchannels that we embedded had what I call an interdigitated pattern, where you have interpenetrating fingers in a sense. And this sort of approach has been used in the past to deliver fluid to electrodes for different types of electrochemical devices, including fuel cells and flow batteries. But in the past, almost exclusively, the dimensions of these flow fields were millimetric in size, meaning that the cross-section of the channels used were greater than a millimeter. We used microchannels. And it turns out that the use of microchannels makes sense in our context because of the particularly low hydraulic permeability of the electrodes that we employ in these systems. I'll jump ahead here and just tell you about some analysis. So what we learned in particular is based on theory, is that the flow patterns that develop inside of these electrodes when they have the microchannels embedded, they depend on a dimensionless parameter defined here that's dependent on the permeability of the underlying porous electrode material, the length of the channels, the width of the channels, and the distance between the channels. Right. And it turns out that provided that our electrode material has a very low permeability, this produces a flow-through configuration between the channels. But when the permeability becomes higher, you get a so-called dead zone in which the velocity is relatively small in between the channels in the center. And then at very high permeabilities, we transition to parallel flow, as it's called, which we don't really want in this system. So we made these things using laser engraving, and this is a nice, interesting part of the work. We found that by soaking our electrodes in water and then engraving them with the laser, we got much better resolution with the laser engraving process, right? So the width of the channels that it's making here are smaller than the width of a human hair. So very small stuff, but that's an easy way to make the resolution really good. And in the end, we end up making a pattern of interdigitated channels that looks something like this on an experimental electrode. Then we incorporate these electrodes into a flow cell in which we direct the fluid in and out of the device using our valve switching apparatus to induce a recirculation in an appropriate way. And when we cycle the device, we use a sequence of alternating current with a square wave, and the voltage responds in the fashion shown here. But if we look at the salt concentration as a function of time in the desalinating reservoir, the salt concentration goes down in a somewhat continuous way. These jumps here are due to the mixing that happens between the desalinated and brine effluents when valve switching occurs. But in short, we were able to demonstrate seawater desalination using this process, like we're demonstrating here, salt concentration as a function of the half cycle number. We're still trying to understand and mitigate the effects of water crossover between the two electrodes through the membrane, and that's why our water recovery rate actually varies from half cycle to half cycle. So we still have a lot to learn. Ultimately, we did show much better thermodynamic efficiency than what was predicted, or I should say, than what has been demonstrated in the past. Even for brackish water feeds, we were able to reduce the energy that results from pumping the electrodes as well, but there's still significant room for improvement in these metrics. So I will just leave you with these conclusions here in the interest of time, and I thank you.
Thank you very much. We don't have time left for questions, but I just want to tell you that I have some ideas on how the work we are doing could complement what you are doing, which is very, very interesting and important. Thank you very much.
Thanks.
And I will like also to introduce now Professor Francisco Cervantes, who's a good friend and colleague. And just to mention that the collaboration between Francisco and myself is a result of last year's meeting. He joined the campus during the pandemic, so we have no chance to meet each other until last year, thanks to this meeting. So in addition of this Mexico-US relationship, these meetings also help Mexico-Mexico interaction. Thank you, Francisco. Welcome, and up to 20 minutes for your talk.
Thank you, Victor, for inviting me to participate in this interesting symposium. I'm happy to share with you this talk. It is entitled Novel Environmental Processes Contributing to Sustainability. So since this topic is related mostly to wastewater treatment plants, so I would like to emphasize that during the last century, we have several technologies which have emerged and are available to treat wastewater, including the activated sludge system and also SVR systems, and the last generation, including aerobic and anaerobic membrane bioreactors. So actually, we have plenty of technologies to treat wastewaters in the world, but yet a large fraction of wastewater is not being treated, especially in developing countries like Mexico. The scenario we have here in Mexico is that roughly 50% of wastewater is not properly treated, but also high-income countries still have some work to do yet. So, but why there is still a major fraction of wastewater which is not properly treated if we have plenty of technologies? So this is mostly related to the high costs associated with the construction and maintenance of these facilities. but also connected to the complex composition of industrial effluent, which make a real challenge for the technologies available to treat these discharges. And the last point is that lately, a lot of recalcitrant pollutants are being discharged, especially from the pharmaceutical, chemical, and petrochemical sectors. So we need to consider these wastewater treatment plants in a different way. Instead of calling wastewater treatment plants, I think they should be considered resources recovery facilities of centers to recover resources during the treatment of water. So I'm going to talk about a few case studies to show you on how some strategies can be implemented to recover some resources during the treatment of industrial wastewater. The first sector I would like to focus on is the piggery sector, and this is related to wastewater which contains a lot of organic matter with the potential to convert this organic matter into methane, into biogas. And this is the case on a major consultancy project I made a few years ago with an association of piggery farms in the state of Sonora in the northwest of Mexico. So anaerobic digesters were implemented in several farms. More than 150 piggery farms installed these anaerobic digesters. And lately, this biogas, of course, is being used to produce electricity, which is relevant because most of these farms are located in rural areas which don't have electricity available. So it's a good way to connect their wastewater treatment with the generation of sustainable energy production, of course. And also connected to this major project is the application of the treated effluent for irrigating wheat crops, and especially because a significant fraction of the nutrients present in these piggery effluents still remain and are available to fertilize these cultivations. And of course, this has to do with the sustainability, because in this way you decrease the demand on fertilizers. So we actually observed that applying this treated effluent for the wheat crops, we significantly increase the yield we observed during the application of this treated water. But coming back to the anaerobic digester, anaerobic digestion topic, you know, this process is a very complex issue involving several microbial groups which need to interact to convert this complex organic matter into methane. And lately, we have been focused on developing conductive materials which promote this direct interspecies lectin transfer among these microbial syntrophic interactions. So we applied these conductive materials during the treatment of this slaughterhouse wastewater, and we observed a significant increase on the production of methane, and also in terms of methane conversion efficiency, and also in terms of organic matter removal, which is technically called chemical oxygen demand removal. And the most efficient material we applied was this organic zero gel doped with graphene oxide. And we are very excited that these materials, which are very cheap to produce in the lab, has the potential to significantly improve the production of biogas from complex wastewaters, right? Another issue I would like to talk about is the recovery of phosphorus, because phosphorus is a major component of fertilizers. It is considered actually a non-renewable resource. And municipal wastewater is a poor source. You know, there is a good content of phosphorus usually in municipal sewage, but many industrial effluents contain a significant concentration of phosphorus. Especially this case that we focused on is this wastewater coming from anodizing processes. which contains more than 4 grams of phosphate per liter. And we developed a precipitating process, which was very efficient on the recovery of phosphorus. And actually, by XRD analysis, we identified the main product in the way that we recover this phosphate in the form of hydroxyl apatite. And this is actually the first report on the recovery of phosphorus from anodizing wastewater. I think there is a great potential to recover this essential nutrient from effluents, such as this coming from the anodizing sector. And we identified this calcium hydroxide as the most effective precipitant agent, and because we achieved 100% recovery of the phosphate in the form of hydroxyl apatite. The last case study I would like to talk is the recovery of metals from metallurgic effluent. This is a very challenging effluent because besides containing a large fraction, a large concentration of metals, including iron, chromium, nickel, and many others, it also contains a high concentration of nitrogen, especially in the form of a nitrate, almost 7 grams per liter of nitrate. The acidity is quite high, the pH is around 3. And also this effluent doesn't contain significant organic matter. So we need to apply the system with 2 goals. The first goal is trying to recover most of the metals present in this effluent, but also to remove nitrate. And to remove nitrate, we apply this denitrifying membrane bioreactor, in which this nitrate is converted to the nitrogen gas, but also alkalinity is produced during the process, and this alkalinity is recycled and received with the influent from the metallurgic wastewater in order to neutralize this water, but also to promote the precipitation of most of the metals present in this effluent. This is a gallery photographs here. This is the membrane bioreactor. This is the precipitating column. And it was very nice to look at this system, which is very efficient on recovering the metals in the form of magnetite, elemental iron, and many other metals, including catalytic elements like zirconium, palladium, and many others. So it was very nice to look at these results. Regarding nitrate removal, we achieved more than 95% of efficiency. So I think, and actually to emphasize that the quality of the effluent that we obtain is ready to be recycled in the sector. So it is very promising. What we did with the recovered metals is to create such a biocatalyst because we added a very small fraction of these metals into anaerobic biomass to start an anaerobic bioreactor in the lab in order to create a biocatalyst to apply this system to degrade recalcitrant pollutants. In this case, is applied to antiviral agents, which, by the way, they were applied against COVID during the last few years. I'm talking about ribavirin and tenofovir. These are the structure of these pharmaceutical compounds. And we observed that the application of a tiny amount of these catalytic metals promoted 100% removal of both for antiviral agents. And we compared to the control reactor containing only the anaerobic biomass with our metals. Well, the efficiency was around 40 and 60% in both cases. So I think there is a significant enhancement on the removal of these pharmaceutical, and we complemented the analysis by the HPLC MS and look at the subproducts coming from the degradation of these pharmaceuticals, and we observed a very good breakthrough of the structure. We observed very small metabolites coming out from the degradation of these pollutants. So it is promising to look at these results. So I will come to my conclusions then, because just to emphasize that wastewater treatment plants should be rather considered as resources recovery facilities. And for that, we need to implement the integrative approaches in order to obtain not only treated water, but also to obtain bioenergy, nutrients, or metals, or any valued byproduct that you can take off this wastewater. And also to consider that process engineering should be combined with novel microbial processes and novel materials in order to improve the bioenergy production during anaerobic treatment. I think there is a lot of work to do also applying environmental processes to mitigate the emission of greenhouse gases. And I didn't talk about that, but in my group, we are also working on developing materials also to prevent the emission of nitrous oxide from different processes. So I would like to thank all the collaborators, especially my students in my group and some other colleagues from other institutions. I would like to give you my contact details here. So, and I thank you for your attention. I hope you have any questions here. Thank you.
Thank you very much, Francisco. I always tell my students that if a good talk is short, it's as twice as good. Thank you very much for keeping on time. And now his presentation is open for some comments or questions. We have like 5 minutes left. Any comments?
Well, I would like to hear a little bit more about Lipata. Can you tell us more about Lipata, please?
Oh, sure. Thank you, Elvira. Thank you for asking that. Well, as Victor mentioned, I joined Lipata, which is this academic unit of the Engineering Institute of UNAM at the Juriquilla campus. Is mostly related to wastewater treatment, but also many research is done focused on bioenergy production, both not only for biogas and biohydrogen, but also in bioelectrochemical systems to produce bioelectricity during the treatment of wastewater. Also, there are some colleagues working with the liquid fuels coming from agricultural wastes. So there's a lot of efforts to produce renewable energy from, in general, I would say from wastes, both from solid waste and from liquid waste, right? What else? Also, and yes, thank you for sharing this slide here. There are some other colleagues looking at the detection of emerging pathogens in sewage. For instance, there was a major study detecting COVID on sewage, which it was very interesting to look at the high correlation, for instance, between the fragments of COVID detected on sewage with the case studies coming from the hospital. So I think it's a good tool to like prevention to take measures when there is an outbreak of COVID or any other emerging pathogen, you know.
Question. Thank you for your talk. I really appreciate the vision there that a wastewater treatment plant should really be thought of as a resource recovery facility. And
thank you.
I think up in Chicago, you may be familiar, there's, I believe that they have phosphorus recovery integrated with the water treatment plant up there. But I just wanted to ask a little bit about some of your approaches dealing with the some of the organic matter where you introduce the conductive agents. Are those, can you tell me more about that? Are those approaches requiring continuous consumption of the conductive agent? How is it that you're sustaining that extra material in the system?
Yeah, thank you very much. It's a good point because the first point is that these materials are produced from wastes. I mean, for instance, we are using activated carbon produced from coconut fiber or any other organic waste, and the organic structure is enriched by magnetite, for instance, nanoparticles of magnetite or graphene oxide, in such a way that you have this network with a lot of particles which with the conductive properties to connect these syntrophic interactions between the microorganisms. And we have tried several doses. We applied, for instance, like 1 gram per liter, but the largest amount we have of us is about 2 or 3 grams per liter. And once you apply it, you can run the bioreactor for 2 or 3 months. It is quite stable. But of course, in a long term, when biomass is reproduced, then you have to withdraw the excess of biomass, and then this conductive material is going out of the system as well. So in this way, you are going to add, but in my opinion, it's sustainable because once it is produced from organic wastes, and secondly, because it's not toxic, right?
Okay. And regarding phosphorus, is your group working with any other contexts on phosphorus recovery other than wastewater, like in contexts where it's not as concentrated?
No, we are mostly focused on concentrated streams, like this anodizing wastewater, but also coming from this digestate, which contains both phosphorus and nitrogen. So I think there is also a great potential to recover these nutrients from digestate coming from the digestion. I mean, talking about the digestion of sludge, right?
Okay, thank you. Yeah, I think we have a number of shared interests. I'd love to talk with you more.
Sure, thank you very much.
Thank you very much. It's time to move on. Now I will ask Dr. Sadir Imiredi to please address the audience.
Right. Hey, can you see my presentation?
Yes, go ahead. Thank you.
Okay. First of all, I would like to thank the I-MMAS team for inviting me today for this talk. My talk might be completely different than what you are seeing so far. So this is just an overview of what research we are doing at the Climate and Atmospheric Science section at the PRI. Ours is a group with who does research identifying and observing environmental flows that happen in our atmosphere, and also do some preliminary model, and also we have a state climatologist in our building. So this is kind of a collaborative research, and I would like to give some brief examples of what we have done so far with the instrumentation and capabilities we have with us. So with that, my talk outline is pretty simple. First, I'll let you know about the motivation of our group itself, why we are trying to study these atmospheric flows, and then we have experience with the multiple types of instrumentation, ranging from ground-based remote sensing to aerial remote sensing and even satellite remote sensing. So I'll give you some brief case study examples of each of these cases. And so for the motivation part, our climate is ever changing. We all can agree with that, but with that change, even the local weather is changing, and the extreme events are getting more extreme and more frequent. So this is a simple climate report given by NOAA for last year. So what you are seeing here is the climate anomalies. That means these haven't occurred usually, but last year they recorded these as the anomalies. They didn't expect them to happen at this magnitude and at these places. So that's why they call them as anomalies, and they have identified a few of them. Based on this, the risk index for each of these locations will change. The risk index is usually calculated by FEMA, the federal authority for looking at the disaster management. So few of these are local weather phenomena you can experience if you're living here, or even if you're living downwind of any Great Lakes, you experience snowfall every year. And some years you might experience some blizzards with tremendous amounts of snowfall, stopping daily operations. Similarly, floods, similarly wildfires and extreme heat events. So we would like to observe locally occurring extreme weather and also locally occurring usual weather to understand more and study the physics of it, so that we can better improve the prediction algorithms or forecast models, which will then improve the accuracy of your climate models. So you can predict the occurrence of these extreme events well beforehand, so that you can be better prepared for them. So with that, I'll jump into the case studies. So the first looking at the atmospheric scales. So this is overview of our capabilities, like what scales are we studying at. So there are many processes happening in the atmosphere, starting with a meter scale that happens, usual turbulence, wind gusting over your face, to a large scale phenomena like hurricanes, cyclones, and even monsoon rainfall, torrential rainfall. So they have their own spatial scale and also temporal scale. So some occurs over a matter of few minutes, few seconds, and some do occur a matter of hours and days. So what we are interested in actually looking at the atmospheric processes occurring in this highlighted window. So that can range from turbulence to thermals to tornadoes and as high as the hurricanes and cold fronts. So for this, we have in the past projects, we have actually used multiple types of observations. Not all observation capabilities are able to see all these phenomena, so that's why I highlighted this. So ground-based observations are two kinds. One, you have the remote sensing observations, and another one is the in situ observations, where you actually place a sensor and just forget about it, and it keeps collecting the data, and then you later study what's happening with the data. And similarly with the remote sensing, you know where to look, you point your remote sensing instrumentation to it, and then you record what's happening in the atmosphere. Similarly, you can actually make them airborne, although it's more expensive. You can actually have a research aircraft, like in the picture shown here, to do both the aerial remote sensing and in situ. So this is to get more data, because with your research aircraft, you can actually cover a lot of land in a short period of time. And if all else fails, if you want to have a look at a bigger picture, you can always rely on the satellite remote sensing, which actually you have these geostationary satellites and geosynchronous satellites that look down onto the Earth, and some are active satellites, some are passive satellites. So pretty much you can see what's going on from far above, so that you can actually get even bigger picture of the weather phenomena happening around us. So as there are advantages and disadvantages with any of the instrumentation, the primary differences between remote sensing and in situ, I'd like to highlight a few of them. First, coming to the advantages of remote sensing, you can actually look far ahead with your remote sensing apparatus, and you can actually look across scales. So like I said, you can look what's happening on a smaller scale, like the wind blowing over a building or wind blowing behind a tree line. And also you can actually look at larger scale phenomena like clouds, or how high the clouds are from the ground surface. And you can, with some infrastructure, you can actually move them from place to place. Like there are few of the remote sensing instrumentation that have been used as mobile laboratories. So it's not quite easy, but it's not terribly difficult as well. So that comes as one of the advantages of remote sensing. Similarly, with the in situ, where it highlights is with the temporal resolution. So you can have a sensor sitting at the same place, and you can record at a much higher frequency. So you can actually look at the much high frequency fluctuations or high frequency turbulence that happens at a given location. And at the same time, you can actually mount multiple sensors on a given meteorological tower. So these towers can be as small as 1 meter to 2 meters and as high as 30 to 40 meters, depending on the application. And you can do a continuous monitoring, as in you can actually leave the sensor, provided you have enough power supply, and you can just keep collecting the data, record the data, and then later study the data. And these are not so terribly expensive because it depends on the type of the sensor, but altogether, it's not as expensive as the remote sensing apparatus. Coming to the limitations, the remote sensing apparatus does require a little bit more power than compared to the in situ sensors, just because of their size and because you are looking far ahead. You need more energy to start the remote sensing apparatus and to send that signal and receive the signal back. So it does require more power, and the atmospheric composition dictates what you actually read back from the atmosphere. So most of these weather phenomena, few of them are visible to our naked eye, but most of them are not. You wouldn't know a cold front passing through unless you actually feel the cold passing by. So it's really atmospheric composition dependent, and major limitation is, like I said, it's really expensive. Coming to the limitations of the in situ measurements, the initial setup of the infrastructure might be a little tedious task because you need to have proper permissions for actually erecting the tall tower, and you need to supply continuous power to the tower. So right now, nowadays, we are using solar panels to power any of the meteorological towers, depending on how many sensors you have. And these are only point observations. So you will only know what's happening at that point, at that time. You may not, using that, you can actually predict what's happening before and after, but you're not actually measuring it. And these are mostly micro scales, so they are only applicable at smaller scales. So, but most of the results that I will show you today are based on the remote sensing LiDAR application. So I'll just briefly give you an overview of how LiDARs work. So LiDARs are light detection and ranging. So you just send a known signal of a known energy, and any of the aerosols or any of the smoke particles or clouds or fog present in the atmosphere will scatter and reflect some light back to the instrument, and it receives and calculates how much energy is reflected back. And based on the difference between the sent signal and the received signal, you can estimate what's it being reflected off of. So using that, you can pretty much detect wildfire smokes, or even clouds, or even fog, or even aerosols emitting from big cities. So the first case study that we are going to look at is the lake breeze. So a lake breeze happens when you have colder air over lake that's actually moving onto the land, which is warmer related to the lake. So this happens in the summer and early fall of places that are downwind of lakes. So here on the right, you can see the Lake Ontario and part of Lake Erie. So a good telltale signal of lake breeze is you will have clouds forming because of the warming air being lifted off of the ground. You will have clouds forming that are right in front of the lake breeze. So that's why you're seeing here in the satellite imagery a clear region just downwind of the lake, but then you have clouds all over the lake here. So these lake breezes are quite common, and they occur every time. To study the lake breeze, and the need for studying the lake breeze is, like I said, because it lifts the warm air from the ground up, it can sometimes enhance the thunderstorms that are forming over the land. So we need to study the lake breeze and how it interacts with thunderstorms. Right side is an example of how a lake breeze interacts with a thunderstorm at Chicago. You can see the lake breeze coming from the Lake Michigan is actually enhancing already existing storm system and making it a severe storm system. So we have a Doppler LiDAR with our group. So the advantage of Doppler LiDAR is, in addition to the backscatter, that is the reflected back energy, you can also measure the line of sight velocity. So when you send a laser beam or when you send a light beam, you can actually measure what's the object that it is reflecting off of, and also if it is moving, you can estimate what is the rate of velocity in that direction. So with that, we actually deployed our Doppler LiDAR downwind of Lake Michigan in Michigan, Holland, Michigan. So we are on the eastern side of the Lake Michigan, and we are looking at the clouds, and also we are looking at the lake breeze as it progresses inland. So with that, we first initially looked at the boundary layer evolution, which is quite easy. As you see from the ground, the warm air lifting up, usually over the day, they reach higher and higher altitudes. So we can sense the boundary layer, how deeper it gets and how it changes over the day. And when scanning cross sections, you can actually see the lake breeze initiating lake breeze arriving towards the LiDAR location. The LiDAR is located at x = 0. and then the lake breeze arrived from west towards the east. So it came and it passed the LiDAR location, and it went 2 kilometers inland before we detected it slowing down. And from this data, you can actually sense how fast that breeze is moving and what is the depth of that lake breeze front. So here is an example of the front progression. So in time, you can actually measure the velocity of the front, how fast it is moving. So this is critical for understanding why or how it enhances the downwind thunderstorms or storm systems. Similarly, by taking multiple scannings, these LiDAR scans are very fast. By taking multiple scannings, we can actually construct a three-dimensional surface of this lake breeze front by detecting the changes along the front where the velocity changes and also where the backscatter changes. So we were able to construct a 3D surface based on that data. So that's one case study. And the second case study is looking at what happens when you have a small-scale wind turbine and when you have urban infrastructure such as a building. So this was done on the grounds of Oregon National Laboratory in Chicago. So we have deployed our LiDAR system behind a building, and then far behind you have a small-scale Berge wind turbine. This is a very small-scale turbine. So our aim is to look at any wake structures that actually were created behind this turbine and if they interact with the building or not. So we were able to see a good formation of wake structures in the form of a deficit in the velocity. So here the wind is coming from left to right, and then our LiDAR is at the here x equal to 0 location. And by looking at the line of sight velocity, we can see the velocity deficit occurring. That actually starts at the top of the building, and then it gets amplified as it goes downwind. So the wake structure is growing bigger and bigger. And depending on the velocity, you can even have velocity reversal. So here the change from red to blue indicates that the velocity is actually going away from the LiDAR and then quickly turning towards the LiDAR. So you have a clear picture of wake identified there. Similarly, when you have winds coming from right to left, even the building is creating some wake zone behind the building. So anything behind this building, these buildings are really small, 20 meters or so in height. So behind the building, it's enhanced turbulence. So it's possible that nothing grows behind this building. So another case study is we are looking at the local agricultural fields where small scale terrain changes might actually be important for local farmers to identify when to disperse their pesticides and chemicals in their field. So we have used actually not one but 3 LiDARs to look at the local nocturnal flows. These are happening at night and early morning. Since these are not visible to the naked eye, we went ahead and released smoke as a tracer. So the smoke being a little thicker than the atmosphere, you can actually detect that through the LiDAR using backscatter. So this is a picture where you have the downslope flow. That means the heavier, colder flow flowing down the slope. And then you were able to detect that using the LiDAR system. So using 3 LiDARs, you can actually construct, just like the lake breeze example, you can actually construct a 3-dimensional picture looking at different cross sections, using all the 3 LiDARs at the same time. And that's been our objective. And we were able to sense that presence of the crop can actually dictate how wide these cold air drainages are in any given agricultural field. Not only with the LiDARs, but we can actually see what's happening with the meteorological towers. We have also deployed 10 to 20 meter towers at strategic locations. We can actually detect the drainage flow flowing down the gully. This is really not visible to our naked eye, and this doesn't happen over a large scale. So this is really small scale phenomena. And if not for the LiDARs, it will be really, really difficult to visualize this flow. The last case study that I'll be discussing is for the lake effect storms. These are the storms that happen during the winter time when the water body is warmer when compared to the landmass. So you have the cold air from the landmass moving over the lake water, and because of the warmth, the lake adds heat and moisture towards that cold air, and it results in formation of clouds filled with snow. And once the cloud passes the lake, it dumps a bunch of snow onto the downwind location here. And they're really important because in 2022 of November, the New York Buffalo location recorded a significant or historical amount of snowfall due to one of these lake effect storms. And these happen at all the Great Lakes where you have water body that is warmer than the upwind location. So you can expect snow, heavy snow on the downwind of these lake locations. So for this project, we used the aerial remote sensing and aerial in situ observations that were collected across Lake Michigan and Lake Ontario that were done about 14 or 15 years apart. So using that information, we can deploy the LiDAR system on the aircraft and look down to detect any clouds that are filled with snow. And you can also deploy the radar that can actually see the snowfall. So from the backscatter of both the LiDAR and radar, you can actually sense what are the cloud heights and also sense what is the snowfall rate. So from combining that data along with the in situ data, we can actually see the snow particle images. And because you know the temperature of the region that you're observing, you can actually categorize them based on at what temperature you see different types of snowflakes forming. And using that, you can start building your empirical relations of because you don't have to have these observations for running the model. So the idea is if you know the temperature of your air, then you'd be able to predict what is the size of the particle of the snowflake and on what are the frequencies of those particles at different diameters. So that's the snow particle distribution analysis we have done. So this is on a rather large scale phenomenon. Continuing with the lake effect snow systems identified at multiple lakes. Now using the satellite remote sensing, you can actually look at the clouds that are forming over the lake and then identify what kind of lake effect are there. So there are primarily two kinds of lake effect that actually forms a parallel to the lake on a long axis and then form a short axis that are perpendicular to the lake long axis. So using a bunch of satellite imagery, you get these daily images at a given time. So you take that and you do the image processing technique to identify whether it is a long axis or a short axis kind of lake effect cloud. So doing this is quite important for forecasters because each of them have different effects on the downwind snowfall accumulation. So identifying that using satellite remote sensing data is quite useful for forecast applications. Now with that, this is just, like I said, this is a brief summary of what we have done so far. And we are really proud of the scales that we have captured. So like I said, like it's shown here, the science across scales. So you have the flows that are happening at orders of tens of meters and going to satellite imagery that can actually record what's happening at orders of hundreds of kilometers. And with that, I would like to thank you for giving this opportunity for speaking here. And I would like to acknowledge my colleagues and my supervisors at the ISWS section. Thank you.
Thank you very much. We will have more time for questions and comments. But to keep it going, let me ask Professor Rafael Tinoco to present his work, please.
Hi, good morning. I'm Rafael Tinoco, an associate professor at the Department of Civil and Environmental Engineering here at the University of Illinois. And we are going to switch gears a little bit, and I'm going to take you from the snow to the beach, to the Gulf of Mexico. And also we're going to change scales from something that we can take from a drone, plane, and satellite to something that we can do in the lab. So I'm really happy to see all of those tools, and I'm going to have to borrow some of those toys later. This project that I'm going to be discussing today is a collaboration that actually started with seed funding from I-MMAS. So this is a collaboration between the University of Illinois and the National University of Mexico. So our co-PI in Mexico, the Dr. Bernardo Figueroa Espinosa, and a large team of people working on the field and in the lab, Cristian Appendini, Alec Torres, Camilo Rendon, Ricardo Quintana, that is now visiting us at the University of Illinois, and students from our own campus, Jihui Wang, and Dr. Chamorro and Dr. Prada, that are also part of the team. So as I mentioned, this is funded by this joint research partnership between UNAM and University of Illinois. So we started this year. So I'm going to be presenting some preliminary data and some preliminary videos that we collected during the field and laboratory campaign this summer. So this is the problem that we are trying to address. So if you have been to the Gulf of Mexico, Florida, Cancun, you might have seen or you might have heard about this problem with sargassum. So these rafts or islands of seaweed that are arriving in larger and larger quantities for longer periods of time to the beach. And if your main source of income is tourism or fisheries, then this really represents some troubles for the community. If that material accumulates, it also creates some health risks. So why sargassum? Yeah, this problem is a really complex one, and it needs to be addressed from a multidisciplinary field of view. So we have biological processes, physical processes, morphodynamic processes that need to be addressed. So we have seen an increase in the arrival of this pelagic sargassum that is damaging the local economy of these areas. And again, it can be attributed to changes in the temperature and changes in the patterns of the currents. So now we see more, this has always happened, but now we see it at a much increased magnitude. So our idea is, can we use what we know about hydrodynamics and aerodynamics and flow structure interaction, plus the biological processes that we can describe with ecohydraulics and ecohydrology, to try to find some new strategies or some new frameworks for prevention, monitoring, or even removal of these sargassum rafts or sargassum patches that go into the beach. So this is just one of the images that we were taking this summer. So you can see this huge island of seaweed, this huge island of something that is alive that is going to be approaching the coast. So we want to try to explore how can we create some framework to try to make better predictions on when it's arriving, how it's arriving, and what can be done to either stop it or mitigate their arrival. So some of the things that other people have noticed is that these sargassum rafts seem to coalesce when they are traveling close to each other. So we need to see how they merge together or how they are spread apart depending on wave, wind, and current conditions. We have seen that their properties change from the time that they are clustering on the ocean to when they are arriving to the beach. And then when we have a large and high energetic effect like a storm, we see that all of this material gets break down and then it can be transported back into the ocean. So you might see a large accumulation from one day, and then on the next day it almost looks clean. So the idea is, can we identify these conditions for current, wind, and wave that will transport and disperse these sargassum patches on the coast? So we are going now to the laboratory where we were running this experiment. So if you're familiar with the coast of Yucatan, this is the beach of Sisal, and the laboratory is right there. So that white building at the end of the picture is the Laboratorio de Ingeniería y Procesos Costeros de la UNAM. So the Coastal Processes and Engineering Laboratory, where they have some impressive facilities, both for laboratory and for field work that we can use for this type of experiments, for this type of campaign. So hopefully you all have a chance once to visit this institution. So what did you do? What did we do? So the whole idea of this talk is from the field to the lab and back again. And we're going to finish before 11:00. So we went to the field. We collected some live sargassum, fresh sargassum from the coast. We were bringing it into the boat with these containers, not much science on it. We then put it on some tanks of salt water so we could keep it alive for long. So it was recirculating, getting fresh salt water from the ocean, so it will last for longer. So it's very delicate with respect to the conditions that it can survive in. So we need to make sure that we didn't alter the actual properties of the sargassum at the beginning of the tests. And once we have it there, we took it to the lab, to a wave, wind, and current flume that is available at the LIPC. So we could test it and we could characterize the properties of the sargassum to see whether or not we can replicate them for other types of studies in our lab. So for example, this is one of the views looking directly at the plant from inside the flume. And later I'm gonna show some of those apparatus that we were using to measure velocities on the air side and on the water side. So if we can use this type of plant in the lab, then we want to test them against different scenarios for different conditions of waves, wind, and currents, because we know that we're going to have a very complex scenario when these things are on the field. And then we were measuring the porosity, the density, the frontal area of the plants to try to characterize them, to see if we can get some proper physical characterization of these plants, then we can use some plastic surrogates or artificial surrogates so that we don't have to, even if I love to go to Cancun every time that we need new plants. We also need to characterize the drag forces acting on these plants based on wind, based on currents, and based on waves. So in order to do all of that, we need to characterize also the hydrodynamics and aerodynamics, the mean and turbulent velocities in air and water, and finally to characterize how the plants are moving depending on that type of forcing, on those wave, current, and wind conditions. So the first thing that we did is take pictures of it, and then try to characterize what is the ratio between the area above the surface and the area below the surface. Why? Because we want to see which part is affected by wind directly, which part is affected by the current and the waves directly, and then how, if we can characterize the shear that is generated at that interface, that can also tell us how these things are going to be moving. So we did that. We took a lot of pictures, and then we tried to get a threshold of those images so that we can go from those raw pictures of the plant, and here we have the portion above the surface and below the surface, and then we can get some binary images when, in this case, yellow is plant, blue is water. We can play a little bit with those thresholds to get a good characterization of the volume, the solid volume fraction, and the porosity of these plants, so we can get some profiles. And what we care about those profiles, because we are going to have different velocities acting at different regions of the flow, so we need to know which is the area that is being impacted by those flows. And then we drop them in the water. So in this case, if we have waves propagating in one direction and wind propagating on another one, we can use our anemometers to measure velocity profiles of the wind. And here I'm showing just 3 velocity profiles of airspeeds of wind that were collected during one of these experiments by Jihui Wang and Ricardo Quintana, that are part of our are in attendance now in this seminar. So you have questions, it's up to them. So we run those experiments, and how do that looks like? So something like this. So if the video is working, you will see that that plant is being subjected to waves that are propagating from right to left on your screen on the direction of the orange arrow. So we can see that it's drifting in the direction of propagation of those waves. And the velocity at which it will drift will depend on the type of plant that we have. You can see that those plants are flexible, so you see a different type of motion at the surface and different motion as you go deeper in the water column. And we see that it's not moving all equally because of the wavelength and because of the properties of those waves. We will see that it seems like it's compacting and expanding at certain times. So waves were the easy one. Then we go for waves and wind. So then we start working with combined flows, and we start seeing some differences on how the plant moves, how fast it moves, and also how we have those different shear at the surface, and we can start seeing some undulations at the free surface of the water because of those interactions between the wind pushing in one direction while the waves are propagating on the opposite one. And I can just stay looking at those videos for a long time, just looking at how the different branches and the leaves of those plants are moving above the surface and below the surface. So you want current. So now we have waves propagating in one direction and current propagating on the opposite direction. So in this case, current is winning. So we see how the plant is moving in the direction of the current, but you can see how different is the pattern as it moves in this direction compared with the previous one. So it seems like it's trying to be swimming against the waves, and it's just plunging and going up, plunging and going up. So if we have larger patches of this material with this type of wave conditions, what will happen to patches that are initially separated? Will they be coalescing, or will they be split up and spread apart by these wave conditions? And then we invite all to the party, and then we have waves, current, and wind. So we have all of these different combined effects to see how the plant moves. Now you can see some more irregularity on the waves because of this interaction between all of those processes. We were so excited that even the camera got a little bit blurred. But you can see the different patterns of motion between the plant as it interacts with the waves, with the current, and with the wind. So we are characterizing profiles, velocity profiles on the air phase, on the water phase, so that we can look in detail at those interfacial stresses to see how the drift is driven by this interaction between those three processes. If we want to look in detail at those interactions, we can zoom in into our plant and use different techniques to characterize those flows. And one of the things that we like to use is to shoot lasers. So we create this particle image velocimetry technique. We didn't create it. We are using this particle image velocimetry technique when we create a light sheet, when we can illuminate the particles in a plane of the flow. So in this case, we can see the waves propagating from left to right. The plant is entering this region that is illuminated by our light sheet. So we can characterize the velocity of all of those particles moving around the plant. So we can see directly the interaction between the plant and the flow around it. And we can do that for many different wave, wind and current conditions. So for example, we go to the limit of our shortest wave periods. You might not see this properly scaled on the field, but you can see the different behavior that the plants will experience depending on the type of flow that they are subjected to. So here you can actually see some rotation even of the plant as the wave is impacting them. Again, this is a very short period. You can see some redirection of that flow even near the bed, but we are still analyzing the data to see how we can scale properly these parameters. So we took the plants from the field into the lab. Now the question is, how do we take this information back into the field to something that people can use to make those predictions and those new frameworks for monitoring and mitigation that we want to establish? So that is our question right now. How can we go from smaller scales back to large scales? And this is some of the work that some of the people participating in this project are doing, like Bernardo Figueroa and Cristian Appendini, trying to identify how to use the information that we are getting on drag coefficient, on wind-edge effect, on drift and coalescence of these sargassum patches to see how we can predict the transport of them based on ocean currents. So if we can get better predictors based on the new information that we are going to try to generate of drag coefficients of plant determined by these three combined flows, and trying to look at in detail at the interaction between different patches, then our small scale findings can inform these large scale models to make more accurate predictions. How do we get that data? Again, we can use some of the tools from our previous speaker and try to get some remote sensing, or we can ask people to help us. And this is a part of the project. It's a community science effort so that people can take pictures of the conditions of the sargassum on different beaches, and then they can upload those pictures so we can analyze them directly on the web. So this is one of the stations that were located right there in Puerto Morelos, in one of the facilities of the National University. But again, that without the help of people, that is just a post on the beach. So what we need is to reach out to people that will be walking through those areas so that they can be our data collectors. So there was part of the outreach activity, and that is Dr. Cristian Appendini on the left, with some activities with local schools. So we can encourage them to, every time that they pass through that area, go and take a picture. Or if you're there during the weekend, just take one picture on that frame, use your phone to load it to the app, and then we have a very robust database so that we can analyze the different evolution of sargassum arrivals during different stages. So we don't need to have a camera or a station permanently located on the beach. People walking there, they can take their data and we can rectify those images to make them useful. So with that, we conclude our preliminary results. As you can see, we are still working on that data. We just collected in the summer. So hopefully at the end of this first year, we can get much more information that can evolve into something of a larger collaboration for longer, so we can address more of the issues that we are finding with these experiments. So these are the emails from the copy-eyes. Again, the list is much longer, but I just want to thank again Elvira and I-MMAS for organizing this event, and especially to all of my colleagues in Mexico for attending this event during a national holiday. So later we can go to celebrate, but for now, thank you. And if there are any questions, I'll be happy to answer them.
On behalf of I-MMAS at the University of Illinois system, I want to thank all the speakers for the meaningful and engaging presentations. I hope this will spark new collaborations, because more discoveries will come if we work together, and then many problems from Mexico and Illinois can be solved. Of course, thanks to our shining stars, Dr. Chamorro and Dr. Castaño. And thank you for your willingness to share your knowledge, for working together for the well-being of the community. Thank you.